The night sky isn't telling the whole truth. All those stars, all those galaxies, they are just the bright spots, the lit-up cities. They are strung along highways. But the highways themselves, the actual structure, that's something else. It's a web, a cosmic web, built from dark matter and gas. And for pretty much all of human history, that structure, that real architecture, has been completely invisible. We just couldn't see it. Now we can. We've mapped it. We've mapped the skeleton of everything. And that changes the questions. The empty spaces between the bright points, they aren't really empty. They hold the framework, and that framework, it dictates the rules. It decides where galaxies form, where stars light up, where planets can even exist. It sets the stage for everything, including us, to realize you're inside something that vast, something you were never even supposed to see. It reorders your sense of place. It changes the feeling of where you are. We've mapped this continent, but what is it? You have to look away from the bright spots. You have to look at the darkness between them. That darkness isn't empty. It isn't nothing. It's the structure. The cosmic web is a three-dimensional tapestry. It's woven from threads of dark matter. Dark matter is invisible. It outweighs all the stars and galaxies we can see by about 5-1. This dark matter is a cosmic skeleton. It forms immense filaments. They stretch across hundreds of millions of light years. Where these filaments cross, they knot together. They form massive clusters, the great cities of the universe. And between the filaments and clusters, there are vast bubbles, almost empty. We call them cosmic voids, so the night sky isn't a flat canvas. It isn't random points of light. It's a view into a sponge, unimaginable scale, a labyrinth of shadow and light. The glittering galaxies, they're just where the gas got dense enough, drawn in by the gravity of this dark skeleton. Dense enough to ignite stars. They're the decorations on the tree, not the tree itself. This whole framework, this web, it has one origin, one profound beginning. It started as the faintest whisper, a quantum ripple in space-time. In the universe's first fraction of a second, gravity took those tiny imperfections. Over billions of years, it amplified them. It pulled matter toward the slightly denser regions. It left the less dense areas to empty out. What began as microscopic wrinkles became grand canyons. Mountain ranges of the cosmos. So when we map the cosmic web, we're not just charting where things are. We're reading a historical document. We're seeing the frozen echo of the universe's first moment. Grown to a scale so vast it contains everything we will ever know. That historical blindness was part of the story. We were looking at the universe with eyes that only saw light. But dark matter is different. It doesn't shine. It doesn't cast a shadow. It doesn't block light. It's perfectly transparent to our traditional senses. Think of a dark room. You want to find a chair. You can't see it. You can't feel for it. But if you roll a marble and it veers off its path, curving around something invisible, you know the chair is there. You've mapped its presence by how it bends the path of something else. That's the trick. We couldn't see the dark matter filaments of the cosmic web. But we could see how they bent the light from galaxies far behind them. That effect is called gravitational lensing. The immense gravity of these invisible filaments acts like a lens, warping the images of background galaxies. By studying thousands, then millions of these tiny distortions, astronomers could trace the outline of the hidden mass. They could draw the filaments. They could see the voids. They were mapping the chair by watching the marble's curve. But this required a shift in perspective. It took decades. We had to stop looking for the thing itself and start looking for its fingerprints on everything else. It was a cosmic detective story. The suspect never appears but leaves a signature in the bent light of distant stars. That was the first real crack in the invisible wall. The moment we began to see the unseen framework holding up the entire cosmic stage. Gravity is a story, and the first chapter was written in darkness. After the universe expanded, it was just a sea of particles, light and dark, almost uniform but not quite. There were quantum ripples from the very beginning. Some regions were a little denser, just a few more particles here, a few less there. An imperfection so small it seems like nothing, but gravity notices. It always does. In those denser patches the pull was stronger, just a fraction. That stronger pull attracted more particles from the emptier zones nearby, which made the dense patch denser. Its gravity got stronger and it pulled in even more matter. It's a feedback loop, a snowball rolling downhill for 13.8 billion years. This is gravity's patient work. It doesn't build cathedrals in a day. It spends eons laying one stone, then another, until a mountain range rises from a flat plain. Those initial specks of extra density became the seeds for everything. They were the gathering points where the dark matter began to clump and stream, drawing in the rivers of gas that would become galaxies. The empty regions, the voids, they weren't carved out. They were just what was left behind when everything was pulled away toward those growing seeds. This is the gravitational tug of war. It defines the cosmic web, a contest between the dense knots and filaments pulling matter in, and the expanding universe trying to pull everything apart. For billions of years, gravity has been winning, weaving that delicate tapestry of filaments and voids we see mapped across the sky. But there's a twist. That same gravity, the architect of all structure, is fighting another war. It's not just shaping the web, it's competing against the fabric of space itself, which keeps stretching and expanding. The fate of the whole cosmic architecture depends on this silent struggle. That gravitational story has something else in it. A hidden part. The cosmic web, this huge structure, isn't made from the stuff we know. It's made of something invisible. If gravity is the architect, then dark matter is the steel. The concrete, it's the framework you never see. It makes up about 85% of all the matter. Everything we are, everything we see, every star and planet, every person, is just a small part of what's there. The rest, almost all of it, is this shadow. It doesn't shine, it doesn't absorb light, it doesn't interact with light at all. The only way we know it's there is gravity. It feels gravity and it exerts gravity. In the early universe, that was enough. Its gravitational pull was the main force. It was the hand that started pulling matter into those first filaments. Those knots, you can think of it like a foundation for a skyscraper. You walk in the lobby, you see the glass, the marble, you never see the steel rebar, the concrete pilings going deep into the bedrock. But without that hidden skeleton, the whole structure collapses. Dark matter is the universe's rebar. We first knew about it not by seeing it, but by its effect. Astronomer Vera Rubin was studying how stars orbit in galaxies. She found something. The stars on the outer edges of spiral galaxies were moving just as fast as the stars near the center. By the laws of gravity, with the mass we could see, those outer stars should have been slow, drifting, like cars on an empty, distant road, but they were speeding. As if held by something with immense gravity, something unseen. There had to be more mass there, a huge halo of something dark around each galaxy. That was the first real clue. That most of the matter was missing from our picture, but its role in the large-scale structure, in weaving the whole cosmic web that came later, that was even more critical. This mysterious substance made the deep gravitational wells, the valleys in space, and ordinary matter later flowed into them, the gas that became stars and planets and us. It was just along for the ride. It fell into the templates, the shapes that dark matter had already carved out. So the glittering galaxies we see at the nodes of the web, they aren't the structure. They are the consequence. They are the lights turned on inside a house. a house whose walls and beams were built long before, from a material we still don't understand. That dark matter skeleton still had to be measured, mapped. We had gravitational lensing, seeing light bend around the mass. But to chart that architecture across billions of light years, they needed something else. They needed a ruler, a standard measuring stick right there in the cosmos, and they found one in a fossil, a fossilized sound wave from when the universe was an infant. Picture the universe in its first few 100,000 years. It wasn't quiet or dark. It was this searing, dense soup, particles and light, a plasma. And in that hot chaos there were tiny ripples, the same density variations gravity would later use. But back then, before gravity could really take hold, those ripples created pressure. Like a stone dropped in a pond, that pressure made waves, spherical sound waves racing out through the plasma. They pushed matter ahead of them, creating shells. Like the air pushed ahead of a speaker, these were the baryonic acoustic oscillations, the first music of the cosmos, a deep, resonant hum. Then something pivotal happened. The universe cooled enough for atoms to form. The light which had been trapped suddenly could travel free. The cosmic fog cleared, and those sound waves caught in the act, they froze. Instantly, the spherical shells of matter, the peaks of those pressure waves, were locked into the distribution of the universe. They left a signature. A specific scale, a preferred distance. That distance is about 500 million light years. It's the fossilized echo of that first cosmic sound. Now fast forward nearly 14 billion years. We look out at the galaxies. They aren't randomly scattered. They show this subtle, statistical preference to be separated by that exact scale. That fossilized sound wavelength, it's as if the universe has a faint, repeating pattern woven into it, a whisper of its first vibrations. By surveying millions of galaxies, measuring how they cluster, astronomers can find that signature spacing. They can see the faint imprint of those ancient shells, and because we know the true size of that standard ruler, that 500 million light-year scale, we can use it as a cosmic tape measure. If the shells appear closer together in our telescopes, it means that part of the universe is farther away, stretched by expansion. If they appear larger, it's closer. This gives us a precise way to measure distances across the cosmos, independent of anything else. It lets us triangulate. It provides the crucial depth perception needed to build a true three-dimensional map of the cosmic web. We're not just seeing where galaxies are on a flat sheet. We're using the echo of the first sound to measure how far away they are, stitching together the invisible filaments and voids in full, breathtaking depth. This fossil isn't just a relic. It's the blueprint scale bar, letting us finally render the invisible architecture in 3 dimensions. We had that ancient fossilized sound wave as a measuring stick. So we could finally start mapping. The first way to map the invisible web was to take a census, a galactic census on a scale that's hard to even picture. That's what projects like the Sloan Digital Sky Survey do. For more than 20 years, a telescope in New Mexico has scanned the sky, not for beauty. For data, its job was to record the position and brightness of hundreds of millions of objects. But for the web, the key measurement is redshift. The universe expands and it stretches the light traveling through it. The light's wavelength gets pulled longer. It shifts toward red. The farther a galaxy is, the faster it seems to recede from us, and the more its light reddens. By measuring this redshift for each galaxy, astronomers can find its distance. It's like a siren on a moving train. The pitch drops as it moves away. Here, the color reddens. That gives us a third dimension, not just where a galaxy is on the flat sky, but how far away it is in the deep past. The Sloan survey did this for millions of galaxies. You plot each one as a point of light in a vast 3-dimensional space, and at first it looks like a swarm, a chaotic cloud, but you add more points. Millions of them, and patterns emerge. The galaxies aren't random. They trace out delicate filaments, They cluster densely at certain intersections. They avoid enormous, empty bubbles. You're not seeing the dark matter directly. You're seeing where the luminous matter, the stars and gas, has been gathered by gravity. It's like a map of towns at night. You don't see the mountain ranges or the river valleys in the dark, but the towns cling to the shores and the passes. Their pattern reveals the shape of the hidden landscape underneath. Each galaxy in that survey is a town on the cosmic slope, and by plotting them all, the ghostly outline of the mountain range itself, the dark matter web starts to appear in the negative space. That was our first real glimpse of the architecture, not as a theory, as a map built from millions of measurements, but this luminous map had a limit. It only showed us where the stars had chosen to ignite. To see the full skeleton, we needed to observe the framework even in the empty places. A map of towns just shows where people settled. To understand the landscape, you need the rivers and mountains that guided them. That's where the theorists come in. They have a tool of immense power. The supercomputer simulation. They take all that survey data as a guide, and they create entire universes inside machines. They start with the simplest ingredients. A nearly uniform sea of dark matter and gas. They set the rules, the laws of physics, mainly gravity. They press play, and they watch for billions of simulated years compressed into weeks of calculation. What unfolds is breathtaking. In simulations with names like Illustris TNG and the Millennium Run, you see the invisible architecture assemble itself from scratch. Those quantum ripples from the beginning, they grow. Gravity pulls the dark matter into delicate streams. The streams merge into rivers. The rivers converge into dense knots. And the ordinary gas, the future stuff of stars, it flows along these dark channels. It crashes into the knots. It ignites. Galaxies spark to life right at the intersections of the web. The simulation doesn't just produce a picture that looks like our maps. It recreates the whole dynamic story. It shows the web breathing and evolving over cosmic time. This is more than a pretty animation. It's a digital laboratory. Scientists can run experiments you could never do in the real universe. What if dark matter behaved slightly differently? You change a parameter and rerun the simulation. Does a cosmic web still form? What if the early universe had more turbulence? You test it. The simulation answers. These virtual universes have become a crucial feedback loop. Observations from surveys tell the simulators what the real web looks like. The simulators then tweak their models to match it more precisely. And once the simulation accurately mirrors reality, it makes predictions. It tells the observers where to look next, what faint signatures of gas should exist in the supposedly empty voids. What patterns should we see in the earliest galaxies? The simulation becomes a guidebook for future discovery. It's a profound cycle. We look at the sky to map the web. We use computers to grow the web from first principles. And when the two match, we know we're not just drawing patterns. We're glimpsing the fundamental rules that built everything, from the first filament to the last shining galaxy. Those supercomputer simulations needed a reality check. We had to prove the map wasn't just a digital mirage. We needed a way to weigh the invisible framework directly, to feel its gravity with our own instruments, and we found it in a cosmic illusion, a trick of light Einstein predicted a century ago. How do you weigh something you can't see? You watch how it bends the path of light from things behind it. That's gravitational lensing. Think of looking at a street lamp through heat rising off a road. The light wavers, the image distorts, the hot air acts like a lens. Now scale that up. The immense gravity of a massive object, a galaxy cluster, a dark matter filament warps space-time around it. It creates a cosmic lens. Light from a galaxy far behind travels toward us, and its path gets bent. The galaxy's image can stretch, it can magnify, it can multiply into arcs and rings. That's strong lensing, a rare, dramatic alignment, but for mapping the broader cosmic web, we use something more subtle. weak gravitational lensing, there's no single dramatic arc. Instead, the dark matter filaments with their diffuse gravity impart a tiny distortion, a systematic distortion to the shapes of millions of distant background galaxies. Each distortion is minuscule, imperceptible, but by surveying vast swaths of sky, by measuring the shapes of countless galaxies with precision, astronomers can detect a statistical signal. They see the collective shearing, the slight alignment of galaxy shapes that points like a compass toward the hidden mass causing it. This technique turns the entire sky into a giant lensing telescope. We're not looking at the dark matter, we're looking through it. By analyzing how it's twisted the light of the ancient universe behind it, we can make detailed mass maps. These maps show the dark matter directly, not where stars have lit up, but where gravity itself is concentrated. They trace the densest strands of the cosmic web. The great rivers of shadow between the galactic islands, they confirm the voids are truly vast and empty. This is the most direct evidence we have for the invisible architecture. It's like we've been given glasses that let us see gravity itself, and when we put them on, the faint sketch from the galaxy surveys snaps into sharp focus. Three-dimensional focus, the skeleton is real, and we've finally learned how to feel its weight. The maps are here. After all the theory, after all the inference, we can finally see it. The invisible architecture, the Dark Energy Survey, it's an international collaboration. They've made these images, they're breathtaking. They cover an eighth of the entire night sky. And they show it not as stars but as a skeleton made of shadow. In these pictures, the universe is in blues and purples, ethereal, and you see these bright white knots. Those are the great galaxy clusters, the metropolises, and connecting them there are these filaments, like delicate threads, like cosmic silk. Those are rivers. Rivers of dark matter flowing through the immense voids. This is the cosmic web. We're seeing it, but it's important to understand. This isn't a photograph. No telescope could ever take this picture. It's a translation, a data sonnet. What scientists did, they took the light from millions of galaxies. The light is warped subtly. That's the weak gravitational lensing signal. They took that distortion, that statistical warping, and they translated it into a map of mass. They painted gravity. The blue in the image, that's the density of the unseen matter. The brighter the blue, the stronger the pull, the stronger the gravity. So what we're seeing is a direct imprint. The imprint of the universe's hidden framework. It's the difference between hearing a description of a cathedral and then finally standing inside, looking up at the vaulted ceiling. The theory predicted this delicate lacework. The simulations grew it in silicon, but here it is, etched across a real volume of the cosmos, a confirmation. Written in the bent light of ancient suns, to see it is to feel a shift. For generations, this structure was a line in a textbook, a graph in a paper. Now it's a landscape, a place we can point to. It makes the abstraction concrete. In the most profound way, we're not just living in a universe with galaxies. We are living inside a web, and for the first time we have a map of our own home's foundations. That map of luminous filaments, it shows something deeper. The web is defined by its emptiness, by the spaces in between. You look at those images, the bright knots and threads are stunning, but they only take up a tiny fraction of the volume. Most of the cosmos, maybe 80%, is something else. It's the void, the universe's empty quarters, these immense spherical bubbles. Some span hundreds of millions of light years. They aren't completely barren. A few lonely galaxies might drift through, like isolated ships on a dark, placid sea, but the density there is almost nothing. A profound near vacuum. If the clusters are metropolises and the filaments are highways, then the voids are the great deserts, the open oceans, and they're critical to the whole structure. Think of them as expanding bubbles. As the universe grows, these vast empty regions stretch faster than the denser web around them. Their outward pressure pushes matter toward the filaments. They sculpt the web from the inside out. The voids aren't passive background, they're dynamic actors, shaping the cosmic architecture through their very absence. That makes them powerful tools for cosmologists because they're so empty, they're sensitive probes. The rate a void expands tells us about the push of dark energy. The overall expansion history of the universe. By measuring voids, we can calibrate our models of the cosmos itself, but they're also unique natural laboratories. Those rare galaxies that live inside a void, they exist in profound isolation. They haven't had a close encounter with another galaxy in billions of years. They evolve in quiet solitude. Studying them is like finding a tree that grew alone in a meadow, compared to one in a dense, competitive forest. It shows how environment dictates a galaxy's fate. In the crowded clusters, galaxies are stripped of gas. Their star formation gets quenched, but in the void, a galaxy can grow slowly, peacefully, preserving its primordial gas. It's a fascinating counterpoint, a glimpse of what a galaxy's life might have been like if it had never been drawn into the bustling urban centers of the web. The void isn't a wasteland, it's a preserve, a place where the universe's quieter, more solitary stories are still being told. This hidden gas, it's the oldest material in the universe. The intergalactic medium, a diffuse, superheated fog, primordial hydrogen and helium, the very first atoms formed minutes after the Big Bang, and this isn't the gas inside galaxies. It's the gas between them, and it doesn't just float there, it flows. It streams along the dark matter filaments of the cosmic web, tracing those invisible highways with a faint, luminous breath. This gas is the lifeblood of the web. It's the raw fuel, the fuel all galaxies form from and grow on. You can picture a vast river system, a continental one. The dark matter filaments are the deep river valleys carved by gravity, and the intergalactic medium is the water, flowing silently through those channels. Destined for the Great Lakes, the galaxy clusters at the intersections, but observing this river is incredibly difficult. The gas is so hot it's ionized. Atoms stripped of their electrons, and it's so thin. A single cubic meter might hold just one atom. In the emptiness of intergalactic space, that's considered dense. It doesn't glow brightly for our telescopes, so how do you detect a whisper-thin fog across a billion light-years? You use cosmic lighthouses, the brightest objects. Quasars. A quasar is the furious core of a distant galaxy, powered by a supermassive black hole. It beams a brilliant, pure spectrum of light across the cosmos. And as that light travels toward us, it passes through the filaments of the cosmic web. It passes through that primordial fog, and the fog leaves fingerprints. Specific atoms in the gas, like hydrogen, absorb very specific wavelengths of that quasar's light. It's like holding a brilliant white light behind stained glass. The glass absorbs certain colors, leaving dark lines in the spectrum. When astronomers analyze the light from a single quasar, they don't see a smooth rainbow. They see a forest of dark absorption lines. Each line is a slice of the intergalactic medium, a single cloud of hydrogen at a specific distance. And because the universe is expanding, light from more distant gas is stretched more, shifting each cloud's fingerprint to a different place in the spectrum. So one quasar's light, having crossed billions of light years, gives us a core sample, a single needle-thin probe through the cosmic web. But if you point telescopes at thousands of quasars, you get thousands of core samples. You can stitch them together. You can build a three-dimensional tomography of the gas. This map is called the Lyman-Alpha forest, and it's breathtaking. It reveals the delicate filigree of the warm and hot gas draped over the dark matter skeleton. It shows where the gas is denser, where it's hotter, how it's flowing. It's an entirely independent way to see the architecture, not by the galaxies it collected, not by the gravity we inferred, but by the primordial material itself, caught in the act of following gravity's blueprint. This ancient fog, the leftover material from creation, it's still tracing the shape of our home. It's the final, glowing confirmation that the web is not just a skeleton. It's a circulatory system, alive with the slow, majestic flow of the universe's first breath. That ancient gas flow tells us something deeper about the web. It's not a frozen sculpture, it's alive, it has a history, a story of change written over billions of years. We see the web now in its mature state. But to understand it, you have to watch it grow, you have to rewind the clock. In the early universe, the web was a delicate tracery, a fine spun lace of dark matter. The filaments were thin, the knots were small, the voids were just starting to form. Then gravity went to work. It has a simple rule: stronger pulls win. The slightly denser knots pulled matter from the thinner filaments around them, and those filaments, in turn, drained matter from the emptier regions. It's a cosmic consolidation, a slow-motion gathering. Smaller streams merge into rivers, rivers flow into mighty channels. This process is called hierarchical structure formation. The small builds the large, so over eons the web coarsens. The delicate lace thickens into a network of massive cords. The great galaxy clusters at the intersections grow fatter, pulling in entire groups of galaxies. And the voids, those expanding bubbles, they stretch wider and emptier as matter gets siphoned away toward the growing walls around them. The universe's architecture becomes more pronounced, more dramatic with time. But how do we watch this happen? We can't wait billions of years. Instead, we use a time machine built into light itself. Remember redshift. The farther away a galaxy is, the longer its light has traveled to reach us. We're seeing it as it was in the distant past. By surveying galaxies at different redshifts, we're looking at different chapters in the cosmic story. We can compare the web nearby, which is relatively recent, to the web far away, which is ancient. It's like having a flip book of the universe's growth. Page by page, epoch by epoch, we see the transition from a nearly smooth, youthful distribution of matter to the intricate, clustered, magnificent metropolis we inhabit today. This is the time dimension of the map. It shows us the web isn't just where we are. It's what we're a part of at this specific moment in a grand, ongoing narrative of construction. A galaxy in a dense cluster, one of those big knots where the web connects. It's almost always elliptical, smooth, red. Its time of furious star formation is long over. It's an aging giant. Then you look at a galaxy out along a filament, one of the cosmic highways. That one's almost always a spiral, a star-forming disk. Blue and vibrant, the difference is stark. It comes down to location, to the flow of fuel. A galaxy is a star factory. It needs a continuous supply of cold gas to keep running. In the dense cluster, that supply gets cut off. The space between galaxies there is filled with a superheated plasma, the intracluster medium. It's incredibly hot. When a galaxy falls into a cluster, moving at millions of miles an hour, it rams into this plasma, ram pressure stripping. It's like driving a car through a heavy downpour. The rain hits the windshield and pushes everything off. The galaxy's own reservoir of cold gas, the fuel for new stars, gets stripped away, blown out into the hot void. Starved of fuel, the galaxy's star formation sputters and dies. It becomes red, passive. Its evolution is over, but a galaxy living along a filament has a different life. It's connected. The filament is a conduit, a pipeline of that primordial intergalactic gas. This gas can flow along the filament's spine, cool, and drip steadily onto the galaxy. A constant, gentle rain of new fuel that allows the galaxy to keep its rotating disk structure. It can form new stars in an orderly fashion in its spiral arms. It stays blue, active. Its supermassive black hole, fed by this same flowing gas, may stay relatively quiet, a steady hum, not a disruptive quasar outburst. The filament provides a location, but it's also a lifeline. So a galaxy's fate isn't written just by the stars inside it. It's dictated by its cosmic zip code. Its address in the vast metropolis of the web decides whether it will be a bustling, productive city or a quiet, retired suburb. To understand any single galaxy, you have to ask where it lives. Is it in a crowded urban center where competition is fierce and resources get stripped away? Or is it on a quiet rural highway with a private supply line delivering fuel right to its door? The invisible architecture of the universe doesn't just house the galaxies, it raises them. It shapes their entire life story from birth to maturity. A story we can read in the light of their stars. That story of galactic growth, of fuel moving along filaments, it has an ending, a final chapter that's already being written. And it hinges on a force that doesn't build structure, it unravels it. That force is dark energy. For billions of years, gravity was the architect weaving the cosmic web. But dark energy is the counterforce. It's a property of space itself that makes the universe's expansion accelerate. It's not a pull, it's a push, a gentle, relentless pressure in the vacuum. And as the universe expands, there's more vacuum. More space means more of this repulsive force. Its influence grows with time. Right now, and for the last several billion years, dark energy has been winning. The expansion is speeding up, and that acceleration has consequences for the large-scale structure. Think of the cosmic web as a vast spiderweb still being woven. Now imagine the anchor points start to move apart faster and faster. The threads stretch, they grow thinner, the tension increases. In the far future, dark energy's influence becomes overwhelming. Its push begins to counteract gravity's pull on the largest scales. The formation of new grand filaments and clusters stops. The universe's growth spurt ends. Instead, the existing web starts to fray. Those delicate filaments, the highways of gas and galaxies, they stretch beyond their breaking point. They sever. The great galaxy clusters, those luminous metropolises, become marooned, isolated islands in an ever-expanding, ever-darkening sea of emptiness. The gas flows that feed galaxies slow to a trickle, then stop entirely. Star formation ceases galaxy by galaxy as their fuel supplies are cut off, not by local violence but by the global stretching of space itself. This isn't a violent end. It's a slow, quiet dissolution, a fading. The magnificent architecture we've learned to see will, over trillions of years, be pulled apart by the fabric it's built upon. But this process gives the cosmic web a new purpose. It becomes our most sensitive instrument for studying dark energy itself. By mapping the web's growth, or really, by measuring how that growth has slowed over cosmic time, we can take the pulse of dark energy. We can measure its strength, test whether it's a constant force or something that changes. The detailed maps from surveys like the Dark Energy Survey, they're not just pictures. They're data points in the greatest experiment of all time, forecasting the ultimate fate of everything. So the web is more than a relic or a map. It's a prophecy written in gravity and light. By learning to read its patterns, we're not just discovering where we are. We're beginning to understand how the story of our cosmic home will end. These future telescopes, they're not just bigger versions of what we have. It's a different way of seeing entirely. The Vera Rubin Observatory, they're building it in Chile. It's going to run a 10-year survey, a movie of the sky. Its camera is as big as a small car, and it will take pictures of the whole southern sky every few nights for a decade. It's going to catalog tens of billions of galaxies. Not just their positions, but how their light changes over all that time. That gives us a map, the most detailed static map of the luminous web we've ever made. A complete census, every town, every village across the entire cosmic continent. But to feel the weight of the invisible structure, the framework, you need to see space itself bending. Subtly, that's the goal for the Euclid telescope from Europe. It's already up there. And NASA and Nancy Grace Roman telescope coming soon. These aren't general observatories. They're precision instruments built for one thing, to measure the shapes of galaxies with exquisite accuracy. They'll look invisible and infrared light, see through dust, find billions of faint, distant galaxies. And by analyzing the tiny distortions in their shapes, that weak lensing signal, they'll build maps of dark matter, with a clarity and a scale we've never had. They won't be inferring the skeleton from the towns. They'll be tracing the skeleton directly in 3 dimensions across a third of the entire sky. This is the start of real cosmic cartography. We're not just sketching continent outlines anymore. We're surveying every mountain range, every river valley, every hidden canyon in the gravitational landscape. The data from these missions will be that precise, that comprehensive. It will test our fundamental theories. Push them to the breaking point. Does dark matter behave exactly as we think on the largest scales? Does the growth of the web over time match our understanding of gravity and dark energy? The maps will be the evidence. They'll either confirm the grand narrative we've built, or they'll reveal cracks in the foundation, pointing toward physics we haven't even dreamed of yet. This isn't just about seeing the architecture anymore. It's about reading the fine print written into the beams. The data from these telescopes is immense. It's not a neat blueprint, it's an avalanche. One night at the Vera Rubin Observatory gives you 20 terabytes of images. That's like streaming HD movies for months non-stop. And that's every night for 10 years, hundreds of petabytes for one survey. It redefines big data. It's not just storage, it's comprehension. How do you find a galaxy in that? Measure its shape, its color, the subtle distortion. When you have billions, you can't have a person clicking through. That would take thousands of lifetimes. So you teach machines to see the sky. You build algorithms, machine learning, to scan the flood. They learn what a galaxy looks like, separate it from stars or camera glitches. They measure redshift from the spectrum, find the distance automatically, and they analyze the shape with microscopic precision, looking for that tiny stretching from weak gravitational lensing. That's the signal of the invisible web, but the signal is faint, buried in noise. There's natural variation in galaxy shapes, atmospheric blur, telescope optics. Pulling the web's architecture from this is like hearing a whisper in a roaring stadium. It needs statistical power. You analyze not one galaxy, but billions. Find the pattern in the chaos. That turns cosmology into computational science. It needs the world's most powerful supercomputers, running for months, doing calculations that were fantasy a generation ago. And it needs global collaboration. Scientists across continents sharing code, building new models, checking each other's results. This big data revolution isn't about hoarding information. It's about a new form of perception, a new way to listen. We're building the analytical ears to hear the gravitational hum of the cosmic web over the static of creation. Turning a blinding flood of light into a single, coherent, three-dimensional plan. The map isn't just an image anymore, it's translation, from the raw language of light into the understood story of structure. This grand map, built from light and gravity, has a hidden subplot. It's about the universe's most elusive travelers, neutrinos. They're the lightest particles that have any mass. Trillions of them are passing through your body right now, every second, and they leave no trace. They come from the hearts of stars, from supernovas, from the Big Bang itself. And they have one defining trait. They barely interact with anything. They're cosmic ghosts. That ghostly nature gives them a unique role in the story of the web. Because they have so much energy and so little interaction, they move across the cosmos at nearly light speed. They don't get caught. When the cosmic web began to form, its gravitational wells, those deep valleys in space started trapping dark matter and gas. But not neutrinos. Their high speed let them just fly over the valleys. They streamed freely. That free streaming had a consequence. It acted like a subtle filter. It smoothed things out. On the very smallest scales of cosmic structure, the clustering of matter became a little fainter, a little less clumpy. The neutrinos, by refusing to be trapped, ironed out the finest wrinkles in the universe's fabric. It's a tiny effect, but in our modern, detailed maps of galaxy distribution, we can see it. By analyzing the precise way galaxies cluster on fine scales, cosmologists can detect that subtle smoothing. And from that measurement, they can do something astonishing. They can weigh the neutrino, not one neutrino, but the combined mass of all neutrino species in the universe. The large-scale structure of the cosmos becomes a detector, the largest particle physics experiment ever conceived. It's a profound connection. By charting the grandest architecture, the placement of galaxies across billions of light years, we are probing the properties of the smallest, most ghostly particles. The map of everything is also a scale, measuring the almost weightless. It ties the fate of galactic superclusters directly to the whisper of a particle that can pass through a light year of lead without stopping. So the cosmic web isn't just a structure we observe. It's an instrument we are learning to play, listening for the faintest notes in the symphony of reality. These maps have their own secrets. As they get more precise, something doesn't fit. The universe on the largest scales might have a preference, a direction. Some studies of the cosmic web, its filaments, suggest they aren't just random. They could be aligned, a preferred axis across billions of light years. They call it the axis of evil, a playful name but serious. It means the early universe might not have been perfectly uniform in every direction, that there was a whisper of a tilt, a kind of grain, set at the very beginning. And that grain grew with the universe, shaping how the whole web is oriented now. If that's true, the universe has a subtle handedness, a cosmic north. That challenges one of our most basic assumptions about how it began. Then the clusters, the big hubs of the web. Our standard model says they should be spread fairly evenly, like foam on a well-mixed drink. But some surveys find hints they might be clumping, that the most massive clusters aren't as randomly scattered as they should be. It's like sprinkling salt and finding the biggest grains gathered in one corner. That could just be a fluke. The universe is vast, our maps still only sample part of it. But if it's real, it points to something deeper. It suggests the seeds for these huge structures weren't the simple ripples we assume. That the early universe's quantum fluctuations might have had more complex patterns, patterns we don't yet understand. There's also a chill in the ancient light. In the map of the cosmic microwave background, the Big Bang's afterglow, there's a large, anomalously cold region, the cold spot. For years, it was a mystery. One explanation ties it to the cosmic web. The theory is that along our line of sight to the cold spot lies a supervoid, an immense, underdense bubble in the web. One of the largest structures imaginable. If that supervoid exists, light from the cosmic microwave background passing through it would lose a tiny bit of energy climbing out of its gravitational well. That's called the integrated Sachs-Wolfe effect. It would make that patch of sky look slightly colder, a shadow, a silhouette of the cosmic web's greatest emptiness cast on the first light. Finding that specific supervoid has been hard, but the search shows how these two great maps, the ancient light and the modern web, are talking to each other. An anomaly in one might be explained by a structure in the other. These aren't failures of our models. They're the most exciting places to look. Every anomaly, every data point that doesn't fit, is a potential window. A crack in our current understanding where new physics might shine through. They remind us our maps, for all their detail, are still provisional, guides to a reality far stranger than we've imagined. The map is not the territory, and the territory, it seems, still has surprises. The maps show us where we are, and it's a humbling place, the Milky Way, It's not at the center of some grand cluster. It's not even on a major filament. We're out on a quiet spur, a suburban part of the cosmic web. We're in a modest group of galaxies orbiting inside the Virgo supercluster. It's the final Copernican step. We aren't at the center of anything. Our position is ordinary, profoundly ordinary, a cosmic mediocrity. For centuries we thought Earth was the center. Then the Sun was, then our galaxy seemed special. Now we see it's just another town on a backroad of a vast, structured continent. But that's not a demotion. It's a kind of liberation, because it means the laws of physics we find here in our quiet corner, they're universal. They apply everywhere across the whole web. Our ordinary location is what lets science work, but inside that ordinary place there's an extraordinary connection. Look at your hand. The atoms in it, the carbon, the oxygen, the iron, they have a history. They were forged inside stars, stars that lived and died long before our sun. But how did those stars form? They ignited from clouds of gas, gas that flowed along the filaments of the cosmic web. That gas was channeled by gravity, by the pull of the dark matter skeleton. It gathered into nurseries where those precursor stars were born, and when those stars died explosively, they seeded space with heavy elements. Elements that would one day become part of us. So you're not just looking at a map of the universe, you're looking at a family tree written across billions of light years. The calcium in your bones, the oxygen in your lungs, the iron in your blood, all of it was stardust, transported across the cosmos by the invisible architecture we're now mapping. We aren't passive observers of this structure, we are its product. We are the universe in one particular place, becoming conscious of itself. Gravity's patient, invisible hand spent billions of years weaving the web. Channeling gas, igniting stars, scattering the elements, all leading to the possibility of a moment like this. A moment where a collection of those recycled atoms on a small planet around an average star can look back and begin to trace the outlines of the home that made them. That's the real weight of the map. It doesn't just show us where we are, it shows us what we are. And how deeply, inextricably, we're woven into the fabric of everything. Our cosmic web is a historical document. It records a unique beginning. The pattern of filaments and voids we see is the direct descendant of quantum fluctuations from the universe's first fraction of a second. Change those initial vibrations slightly, and you get a completely different architecture, a coarser web with thicker, fewer filaments, or a finer, more delicate lacework. Or maybe a universe where matter never clumped into filaments at all, just a diffuse, lonely haze, and that leads to a staggering thought. If our universe's starting conditions were just one possibility among many, could there be other cosmic histories? Other webs. This is where the map of our home touches the most speculative idea in cosmology, the multiverse. In the theory of eternal inflation, our entire universe is one bubble in a frothing, infinite sea of spacetime. Other bubbles, other universes, could have inflated under different rules, different fundamental constants, and crucially, different patterns of those initial quantum seeds. In those other realms, the cosmic web, if it forms, would be unrecognizable. Their large-scale structure would be their own unique fingerprint, a direct imprint of their own distinct birth. So by mapping our web with greater precision, by characterizing the exact statistical properties of its filaments and voids, we are doing something profound. We are cataloging the unique signature of our universe's genesis, reading the identity card of our particular cosmic bubble, and this provides a fragile, theoretical bridge. A bridge between the observable architecture we can measure and the utterly untestable concept of a multiverse. We cannot see those other universes. We may never prove they exist. But by understanding our own web in exquisite detail, we can at least say, this is what our universe's beginning looked like. And in doing so, we define the one reality we know against a backdrop of infinite possibility. Our map becomes more than a guide. It becomes a birth certificate for everything. That birth certificate is written in patterns, patterns we can only talk about by using things we already know. To really get the cosmic web to feel its shape, we need metaphors. They're the bridges between what we can't imagine and what we can. One strong comparison is to a neural network. You picture the universe as a giant brain. The galaxies are the neurons, and the dark matter filaments connecting them, those are the axons, the long fibers that carry signals. They transmit influence, gravitational information, across all that empty space. It's a thought that changes what connection means. It suggests the universe might be arranged in a structure that mirrors the very thing trying to understand it, the brain itself. Other people look at the maps and see something more physical, a huge sponge, the dense clusters and filaments, that's the solid material. The giant voids are the hollow pockets, the air. The universe isn't a solid block, it's porous, it's an intricate matrix, or you can think of it as froth on a vast, churning ocean of spacetime. The bubbles, the voids, they're stable, and the thin walls of froth between them, the filaments, they trace out this delicate architecture. It's ephemeral. You can even see the web's signature at home, in your kitchen. Imagine heating a thin layer of oil in a pan. The oil warms from below and it starts to convect. Hot, less dense oil rises in narrow columns. Cooler, denser oil sinks in the spaces between. It creates a stable, repeating pattern, interconnected lanes. A cellular web of rising and falling fluid. It's a direct example, you can see it. It shows how differences in energy and density, driven by a simple force, can self-organize. Into a complex network, the cosmic web works on the same principle. Gravity is the heat source, dark matter is the fluid, but it's sculpted over billions of years, not minutes. These analogies, they aren't just poetry, they're vital tools for thinking. The true scale of the web, its nature hundreds of millions of light years across, made of invisible matter, it defies everything we know from daily life. Our brains evolved for a world of trees and rivers and horizons. They have no built-in framework for a gravitational tapestry woven across all of existence. So we borrow from the world we know, we compare it to a sponge, a brain, a simmering pot. These metaphors give our intuition a handhold. They let the profound become not simple, but at least somewhat comprehensible. They translate the cosmic map into a story our senses can follow, and they let us feel, in a small way, the architecture of where we live. That translation from data into experience, it's a creative act. It needs an artist's eye, because what comes out of a supercomputer simulation isn't a picture. It's a vast spreadsheet, just numbers, positions, densities, velocities for billions of particles. To turn that into a visual journey through the cosmic web, scientists work with visual artists, data visualization experts. That collaboration is where science meets narrative. And the artist's task is immense. They have to take terabytes of cold, numerical data and render it into something the human mind can navigate, something that feels like a place. The decisions they make are aesthetic but also deeply scientific. Like, what color should dark matter be? It has no color, so they choose hues that convey meaning. Often deep blues and purples for mass density, bright gold or white for the hottest gas, the most luminous galaxies. They decide on the camera path. Do you fly through a void to emphasize the emptiness? Or race along a filament following that river of gas? Each choice highlights a different scientific truth. The lighting, the texture, the sense of scale, all crafted to be accurate but also emotionally resonant. These aren't cartoons, they're rigorous interpretations. Every galaxy in the scene is placed based on its real, simulated coordinates. The flow of gas follows the actual gravitational currents from the data. The artist is a translator, working with the scientist to make sure the final image tells a true story, and that translation is vital. it creates a shared language. When you sit in a planetarium and watch a fly-through of the cosmic web, you're not just learning facts, you're going on a voyage. You feel the sheer scale as you pass a galaxy cluster, something that takes millions of years to cross in a blink. You sense the delicate structure of the filaments like threads in a grand tapestry. That emotional, visceral understanding, a graph or a research paper struggles to deliver that. It fosters a public wonder, something essential. It reminds us the universe isn't just a set of equations to be solved. It's a sublime reality to be explored. And through this artistic lens, the invisible architecture becomes a landscape, something we can all, for a moment, call home. That artistic journey through the web is grounded in a physical reality. And we can measure it in another way. To find the universe's most energetic neighborhoods, you don't look for light, you listen for its echo. This method uses an interaction between the oldest light and the hottest gas. The cosmic microwave background radiation, that ancient afterglow, travels across the cosmos. Its journey isn't always undisturbed. If its path takes it through a massive galaxy cluster, it passes through a superheated soup of electrons. These electrons are incredibly energetic. They move at nearly the speed of light. So a microwave photon from the ancient background passes by. It can collide with one of these hot electrons. In that collision, the photon gets a tiny kick of energy. It shifts to a slightly higher frequency. That process is called inverse Compton scattering. Its imprint on the cosmic microwave background is the Sunyaev-Zel'dovich Effect. It creates a specific, cold shadow in the ancient light, a shadow that points directly to the location of that immense cluster. Telescopes like the South Pole Telescope and the Atacama Cosmology Telescope are built for one purpose: to scan the sky for these minute distortions. They map the cosmic microwave background with exquisite sensitivity, looking for those cold spots. Each spot is a signpost, a marker for one of the universe's most massive structures. This technique is powerful because it doesn't depend on brightness, not invisible light or X-rays. It works purely on the mass and heat of the gas itself. So even a distant, faint cluster, if it's massive and hot enough, will leave this shadow. It's like finding mountains by the long, cold shadows they cast at sunrise. By surveying the entire sky for these shadows, astronomers build a census of the web's grandest hubs. They trace the distribution of the most energetic material. This map is painted in the negative space of the universe's first light. It complements the others perfectly. It shows where gravity has gathered matter so densely it's been heated to millions of degrees. It highlights the intersections of the cosmic web's mightiest filaments. So we have multiple senses for this invisible architecture. We see where galaxies have gathered. We feel the gravitational lensing distortion. We trace the flow of cool gas. And with this technique, we sense the searing heat at its densest knots. Each method reveals a different layer of the same structure, allowing us to perceive the full complexity of our cosmic home. We have the skeleton mapped. We've seen its shadow, but the actual substance of the web that's been out of reach. The filaments aren't empty. They contain a gas, a diffuse, superheated gas. That's the warm, hot intergalactic medium. It's the last missing piece of the cosmic inventory. For decades, our models have said it has to be there. Ordinary matter has to flow along these dark channels to feed galaxies. But detecting that flow directly, that's been the challenge. This gas isn't cold. It isn't dense like the clouds inside galaxies. It's been heated by the huge gravitational shocks from the web's formation. Temperatures in the hundreds of thousands of degrees, millions of degrees. At that heat, it doesn't glow in visible light. It whispers in X-rays. A faint, diffuse X-ray glow spread across these vast, thin filaments, and it's drowned out by the bright point sources, black holes, galaxy clusters. It's like trying to hear one conversation in a roaring stadium. Our current X-ray telescopes, they're powerful, but they're not sensitive enough. They can't pick out this specific, whisper-thin signal from the background noise. We've gotten hints, tantalizing excess emission between clusters, but not the map, not the high-resolution map we need, so the gaseous highways, they've stayed theoretical. Lines on our gravitational maps, their material content inferred but not seen. This is the frontier now, the quest to turn those theoretical lines into illuminated rivers. Rivers of real, observed matter. The goal isn't just to map where the gravity is anymore. It's to light up what's flowing because of it, to see, for the first time, the ordinary matter caught in the act. Following the dark blueprint, that shift it would change everything, from an architectural plan to a live portrait, a portrait of the universe's circulatory system. The mission to do this is already underway, and it hinges on new eyes, a new generation of eyes designed to see the faintest heat in the cosmos. We've always looked out into space for signs of life. But maybe we should look at the map, the cosmic web. It's more than just galaxies. It's like a zoning map for the universe, and its invisible lines might decide where life can even get started. This huge structure sets the large-scale environment for every galaxy inside it. It sets the stage for the planets that form around their stars, where a galaxy sits in the web, whether it's in a dense cluster or out on a quiet filament, that shapes its chances for life. Take a galaxy cluster, one of those big knots in the web. It's a crowded, chaotic place. Galaxies whip past each other, gravity tearing at them. The space between is filled with searing plasma. Radiation floods in from supernova, from black holes. For a planetary system there, the challenges are huge. A nearby supernova could strip a planet's atmosphere. A close encounter could fling it from orbit. The stability life needs, over billions of years, it's under constant threat. These galactic downtowns are brilliant to look at. But they might be deeply hostile to biology's long, delicate processes. Now picture a galaxy on a filament, the cosmic suburb. It's connected to the web's flow of resources, but insulated from the worst chaos. It can draw a steady supply of gas from the filament. That fuels a gentle, sustained rate of star formation. Its spiral structure stays intact. Its planetary systems aren't disturbed by collisions. In this quieter neighborhood, a star like our Sun could orbit in peace for billions of years. Its planets enjoy a stable gravitational environment, so the cosmic web might create these galactic safe zones. Places where the early universe's tumult has settled into a rhythm calm enough for chemistry to become biology. Our own Milky Way is in a place like that, on the outskirts of a cluster in a quieter group. Our existence might be tied to that specific, placid architectural setting, but the web's influence goes deeper than just stability. It also governs the distribution of the ingredients for planets and life. The heavy elements. In the first minutes after the Big Bang, there was only hydrogen and helium. Everything else, carbon, oxygen, nitrogen, iron, all that was forged later in stars and in their explosive deaths. This enriched material, what astronomers call metals, it had to be scattered, and the cosmic web was the distribution network. When a massive star goes supernova inside a galaxy, the explosion blasts these new elements out into space. That enriched gas becomes part of the filamentary flows. It circulates through the web. Over cosmic time, this process seeds younger galaxies and new stars with the building blocks for rocky planets and for life's chemistry. A galaxy isolated in a void, cut off from these highways, might stay impoverished. A place of ancient, metal-poor stars with few rocky planets. A galaxy in the thick of a cluster might be enriched too quickly, too violently, its planets bathed in radiation. But a galaxy positioned along a filament like ours gets a measured, continuous delivery of these vital materials. It's a Goldilocks scenario orchestrated by the large-scale structure of the universe itself. The web doesn't just house galaxies, it manages the cosmic economy of elements. It decides which neighborhoods are rich in planetary potential and which aren't. That connection changes the map of the cosmic web into something new, a guide for astrobiology. As we learn to read its patterns better, we might one day identify the most promising cosmic zip codes in the search for other civilizations. We could prioritize our search not just on stars like our Sun, but on galaxies sitting in the web's most life-friendly corridors. This grand, invisible architecture we've worked to reveal it might finally point us toward our cosmic neighbors. The answer to whether we're alone might not just be written in the chemistry of a distant atmosphere. It might be written in the gravitational blueprint of the entire universe. We have this incredible map of our home, but it comes with a limitation, a quiet truth. We only have one viewpoint. We're anchored here in this one spot in space and time. The light we collect can only travel so far in the universe's finite age. That creates a horizon, an observable sphere. Beyond it, no signal has had time to reach us. So even with telescopes that see billions of light years, we're surveying a finite volume. It's a sample, and any sample, no matter how large, can have its own quirks. Statisticians call this cosmic variance. It's the possibility that the pattern we see, the filaments and voids from our galactic suburb, isn't perfectly average. That our local slice might be slightly denser or slightly emptier than the true cosmic mean. Imagine trying to understand the global climate with just one weather station. In a single valley, you'd get incredibly detailed data about that valley, its wind patterns, its rainfall, its temperature swings, and from that, you could infer a lot about the larger atmospheric system. But you couldn't know for certain if your valley was unusually rainy or peculiarly calm compared to every other valley on the planet. Your view is inherently local. Our situation is similar, but on a scale that's hard to grasp. The grand web we map with such precision, its specific arrangement of superclusters and immense voids, might just be our local valley. Within the greater cosmos, the statistical properties we measure, the average thickness of filaments, the typical size of voids, could have a margin of error. Not from our instruments, but from our single, fixed perspective. This isn't a flaw in our science, it's a fundamental limit, written into the nature of observation itself. It means as we push our measurements to greater precision, to test our most fundamental theories, we'll eventually bump against this wall, cosmic variance. We cannot know if the largest structure we see, like the possible cold spot supervoid, is a rare anomaly or a common feature. Our maps, for all their breathtaking detail, are ultimately a survey of our local cosmic province. The full majesty of the universal architecture, in all its possible variations, may extend in patterns and scales we cannot yet see, beyond the current horizon. This realization isn't a discouragement, it's a form of humility. It frames every discovery not as a final answer, but as a detailed postcard from our particular neighborhood. In the infinite, this realization that our view is local, it doesn't take away from the map's power. It actually fuels a new kind of education. The cosmic web is becoming a classroom. For the first time, we can teach the structure of the universe not as a theory, but as a place you can actually visit. There are interactive simulations built from the same supercomputer data that guides research, and they let students pilot a virtual ship. They can fly along a dark matter filament, watching galaxies stream past like streetlights on a cosmic freeway. They can plunge into a void and feel that profound emptiness stretch for millions of virtual light years. This isn't just a video, it's an experience. It turns abstract terms like large-scale structure into a navigable landscape, a landscape you remember with your senses, not just your intellect. That tangibility extends into the physical world. Researchers and educators are creating three-dimensional printed models of dark matter distributions. You can hold the cosmic web in your hands, feel the dense knots of clusters, trace the delicate bridges of filaments with your fingertips. This transforms an invisible, mathematical concept into a tactile object. For a student grappling with the scale of it all, holding that model makes it real in a way a textbook diagram never could. It grounds the most immense architecture imaginable in the simple, human act of touch. This approach weaves a single, coherent story. Before the cosmic web, cosmology education often felt like a series of disconnected chapters. The Big Bang was one topic. Galaxy formation was another. Dark matter was a puzzling sidebar. Now they're all parts of one narrative. You start with the quantum ripples of the beginning. You watch gravity amplify them into a dark matter skeleton. You see gas flow along that skeleton to form galaxies. The web is the through line. It connects the first instant to the present day with a clear, visual logic. A student can follow the story from the first whisper to the glittering metropolis we see today, understanding not just what happened, but how each step caused the next. By anchoring education in this cutting-edge discovery, we do more than convey facts. We inspire a different kind of curiosity. We're not just teaching students about the universe. We're giving them the tools to see it as it truly is structured, dynamic, deeply interconnected. This doesn't just create the next generation of astronomers. It cultivates cosmic cartographers ready to chart the unknown territories on our maps. It invites philosophers to ponder our place within this grand architecture. And it empowers every learner to look at the night sky and see not just points of light, but the magnificent, invisible tapestry that connects them all. The greatest lesson the web teaches is that to understand our home, we have to first learn to see its hidden frame. Our map of the cosmic web is a still image. A snapshot of one moment in a 13.8 billion year story. But the universe moves, it breathes, it flows. Galaxies aren't fixed. They're travelers moving along the gravitational currents of the filaments toward the clusters. To understand this, we need more than a snapshot. We need a movie. The goal is a four-dimensional map, adding motion to space. That means measuring not just where a galaxy is, but where it's going. Astronomers call that its peculiar velocity, the galaxy's true motion through space after you subtract the overall expansion of the universe. It's like leaves on a river. You see the broad current carrying everything that's cosmic expansion, but then you see individual leaves twirling, catching eddies, moving a little faster or slower. That's the peculiar motion. For a galaxy, that motion comes from the local gravity. It's being tugged by the filaments and clusters around it. By mapping these velocities for millions of galaxies, we could trace the flow. We could see rivers of galaxies streaming toward the great knots. We could watch gravity sculpting the large-scale structure. To do this requires a leap. Future surveys like the Mauna Kea Spectroscopic Explorer aim to measure redshift for tens of millions of galaxies. But with such precision, they could detect the tiny Doppler shifts from peculiar motion. It's an immense challenge, like trying to measure the speed of a car a million miles away by the faint change in color of its headlight. But if we can do it, the reward is a revelation. We wouldn't be inferring the web's dynamics from simulations anymore. We'd be observing them directly, watching a supercluster gather its material, seeing a filament tighten, channeling galaxies like a cosmic funnel. This four-dimensional map would be the pinnacle. It would test our entire understanding of gravity, dark matter, dark energy. Our models make specific predictions about how matter should flow on these colossal scales. A dynamic map would either show that flow exactly as predicted, confirming the narrative, or it would reveal a discrepancy, a subtle tug in the wrong direction. A flow that's too fast or too slow, that discrepancy would be a beacon, pointing to a flaw in our fundamental physics, telling us that gravity, or dark energy, or dark matter itself behaves differently on the largest scales than we thought. We'd be watching the universe's architecture not just as a structure, but as a working machine, and by charting its every moving part, we would finally understand the engine that built our home. That map of galaxies flowing through space, it shows a hidden geometry. You look at the cosmic web from the biggest superclusters down to the smallest knots, and a pattern repeats. It's not a perfect echo, it's more like a whisper of similarity across all these different scales. The universe has a kind of symmetry, not like a snowflake. A deeper symmetry, a rugged symmetry of form. That's the principle of self-similarity. It's what you see in fractals. A fractal is a shape where, if you zoom in on a small piece, it looks like the whole thing. A coastline looks jagged from an airplane, and it looks just as jagged from a few feet away. The cosmic web isn't a perfect mathematical fractal, but it has that fingerprint. A massive galaxy cluster isn't a smooth sphere. You look closer and you find smaller clusters orbiting inside it like planets around a sun. You zoom into one of the great filaments and you see it isn't a simple rope. It's often braided, made from smaller strands, subfilaments, each one channeling its own flow of galaxies and gas. This nesting, this hierarchy, it continues down. It suggests the process that built the web. It doesn't favor one particular size. Gravity's instability is scale-free. The same rules that pulled a few stray atoms together in the early universe, they also govern the assembly of superclusters a billion light-years across. Those initial tiny ripples, they were amplified at every scale all at once. That's why the map feels so intricate, so deeply textured, no matter how far you zoom in. It's a signature of the process, a signature written in the distribution of matter itself, and by studying these scaling relations, how the number of structures changes with their size, cosmologists can test the physics of the primordial universe. The mathematical pattern of the web today, it encodes the nature of those first quantum seeds. So this isn't just about beauty, though there is a profound aesthetic here, order emerging from chaos. It's about a hidden code, a geometric language. It translates the simple, relentless law of gravity into the breathtaking complexity we call home. The universe may not be a perfect fractal, but in its layered, nested design, you see the elegant, scaling hand of its single, silent architect. The map we made, it has a weight to it. You look at this lattice, this immense structure, and you see where we are. And that brings a kind of responsibility. It's not about rules or belief. It comes from just seeing the perspective. The cosmic web shows a universe of incredible scale, everything connected. And in that, our planet is a speck, but on that speck something happened. Matter became aware. It became aware of the structure it's part of. That's a kind of singularity. We are, as far as we know, the universe understanding itself. That awareness is a rare gift, and it comes with a duty, a form of stewardship. That stewardship starts with a humbling fact. Against the backdrop of filaments and voids, billions of light years across, Earth isn't just small, it's fragile. The conditions that let life appear here, that let consciousness evolve to map the cosmos, that's a delicate chain of events. A very narrow window, the cosmic web shows the grandeur of the stage, but it also shows how precarious our little corner is. Seeing that fragility, it's not for despair. It's the basis for care. It pushes us to preserve the conditions, the stable climate, the rich biosphere, the peaceful orbit, the things that let this project of understanding keep going. Our science, the tool we use to map the web, it has a dual purpose. It's a search for knowledge, yes, but it's also a tool for planetary well-being. The same rigorous thinking that untangles dark matter filaments can model climate systems, manage resources, solve human problems, using knowledge to better humanity and preserve our home. That's the practical form of stewardship. It's how we honor our position. We're not just passive inhabitants of a node, we're custodians. In the end, this cosmic awareness changes how we see our own world. Knowing you live in a vast, structured metropolis of galaxies, you'd think it makes your street seem small, but the opposite happens. It creates a deeper wonder. That this one planet around an ordinary star in a quiet part of the Virgo supercluster could produce beings who trace the outline of their cosmic home, that's a miracle. A miracle worth protecting. Every forest, every ocean, every city becomes more precious, not less, when you see it as part of this grand network, knowing the web doesn't distance us from Earth. It binds us to it more closely as the one place from which we can look up and comprehend the whole tapestry. Our responsibility is to keep that vantage point clear, to make sure the light of understanding keeps shining from this tiny, precious node in the dark. We've been mapping the invisible architecture of the universe. And what we're finding is a cosmos that's far more structured than we ever imagined, more dynamic, more interconnected. It's not just a new fact, it's a new way of seeing. For generations, we looked up at scattered lights. Now we see a tapestry woven from dark matter, lit by galaxies, a structure so immense it holds all of history in its threads. From the dark matter scaffolding we see through gravitational lensing, to the gaseous highways traced by quasars, the cosmic web isn't a theory anymore. It's a mapped reality. We've felt its gravity bend light. We've heard the echo of its formation in the spacing of galaxies. We've watched it grow in supercomputer simulations. Simulations that match the night sky with uncanny precision. This work ties the smallest particles to the largest structures, the universe's fiery birth to its uncertain future. The ghostly neutrino and the vast supercluster are part of the same story. The quantum whisper of the beginning and the silent push of dark energy are chapters in the same epic. Every layer of discovery connects. It reveals a universe that's coherent, governed by elegant rules. Even if they're mysterious, it redefines our address. We're not at the center of anything. We're residents of a quiet spur on a filament, in an ordinary group within a vast supercluster. And from this unremarkable vantage point, we've done something remarkable. We've traced the outlines of home. We've become cartographers of the invisible. As our maps get more detailed, remember each point of light is part of a grand design. We are the cartographers of this hidden realm. It's a profound shift. We're not just inhabitants of a world, we're conscious participants in a universe that is structured, alive and